Thank you for the introduction. Thank you all for being here. And I'd like to extend a very large thank you to the event coordinators for inviting me to give this talk today. My name is Olivia Curtis. I'm a graduate student at Boston University. I've been working with my PhD advisor, Professor Teresa Brainerd, examining how the properties of galaxies within, how the location of a galaxy within the cosmic web can affect its overall global observable properties. Today I'm going to be presenting results from one of the projects in my dissertation looking at how the properties of galaxies within voids differ from those in typical field regions of the universe. So the contents of this talk today is going to be three parts. I'm going to start with a very brief introduction to the large-scale structure, talking about cosmic voids and what we know about matter within voids, before transitioning to talk about my own experiment, examining the properties of voids and void galaxies within the TNG300 simulation, and then concluding with the results of my experiment. So the first spectroscopic redshift surveys of the 1970s showed that when we look out into the universe, we don't see galaxies distributed randomly. Instead, we see them in this interconnected network of nodes and filaments that has today colloquially become known as the cosmic web. Within the cosmic web, there are really three environments that we can locate galaxies, those being galaxy clusters, or the largest gravitationally bound objects in the universe. Connecting those clusters, like lines connecting dots, are walls and filaments. And then between these regions are vast, nearly spherical, nearly empty regions of nothingness known as cosmic voids. Cosmic voids truly are some of the largest and emptiest regions of space that we can observe. Here's results taken from the Dark Energy Survey's void study, where on the y-axis we're plotting the number density of galaxies within voids, normalized by the total number density of galaxies in the simulation as a whole, in the survey as a whole, as a function of void radius. And what Desi found was that indeed the interiors of voids are truly underdense in galaxies compared to the average of the survey, but not completely empty, with this concentration of galaxies increasing up to a maximum just beyond one void radius. That's what's known as the wall or the ridge of the void, or the location around the outskirts of the void that all matter interior to the void is gravitating out towards, before leveling off to the average of the simulation out to, or survey out to larger void radii. What Desi reported was in their 140 square degree survey, they found 87 voids with an average radius of about 37 H-inverse megaparsecs, maximum void size reaching 120 H-inverse megaparsecs, with an average angle on the sky of about 1.5 degrees, out to an average redshift range of z equals 0.57. So these voids are underdense, yes, but they're not completely devoid of matter. So voids themselves still show some of their own significant substructure. So here's another spectroscopic redshift slice taken from the Sloan Digital Sky Survey, where we can see some features in the local universe that some of us might be familiar with, such as the Coma Great Wall, the Boot Supervoid, the Ursa Major Void, etc. If we take just a look at the Boot Supervoid, we can see that yes, although the center region of this void is very much underdense compared to the average of the survey, there's still some diffuse networks of walls and filaments with interior to this void that sort of act as cosmic flow highways that bring matter interior to those voids and connect it to the rest of the cosmic web. So where there's structure, there's bound to be gas and subhalos and galaxies within there. So one of the largest observational surveys looking at the properties of galaxies within voids was led by Krekel et al., which provided detailed H1 imaging of around 60 void galaxies and some of their companions, taken from Sloan Digital Sky Survey data. On the right here are some example thumbnails that they provide of some of their target galaxies. And what they find were that void galaxies are gas-rich, contain typical H1 masses for their luminosity, are actively star-forming, and show evidence of ongoing gas accretion. Now, I'd like to say that this is definitive proof that void galaxies clearly undergo different evolutionary pathways, but since this study, there's been a large body of work, kind of contradictory work, both in observations and simulations, stating whether or not these galaxies within these voids should actually show these different features, such as being bluer or more actively star forming on average. So with that, I wanted to conduct my own experiment using state-of-the-art magnetohydrodynamical simulations, looking at whether or not within the z=0 snapshot of the TNG300 simulation, we can see any differences between galaxies within voids and galaxies in typical field regions of, or typical filamentary regions of the universe. So the TNG project is a suite of cosmological magnetohydrodynamical galaxy formation simulations. The suite contains 3 simulations of volumes 50, 100, and 300 cubic megaparsecs respectively, where TNG300, which is the one that I'll be using in my study today, contains well over 2,500 cube dark matter and gas particles, 10 to the 5th black hole particles, and around 10 to the 8th stellar particles. The purpose of this simulation suite was to simulate the formation and evolution of as realistic looking galaxies as possible. And TNG300 was chosen for my study because it provides a large enough spatial size for me to get a large enough sample of voids and void galaxies with which to perform statistics with. So here's actually a visualization I made of the TNG300 simulation box. So here I'm showing 2D dark matter density maps panning up through the simulation box, so panning up through the z-axis of the simulation, with blue showing regions of larger dark matter density, red showing regions of lower dark matter density, and white showing regions or densities in between. I really like this visualization, not just because it's mesmerizing to look at, but because it also shows the true interconnectedness of the cosmic web as a whole. If you choose your favorite underdensity region, you can also see that substructure that I was talking about earlier, where each of these voids sort of have their own tributary network of smaller diffuse filaments that work as pathways to feed the material inside of those voids out to the rest of the large-scale structure. So next, going on to talking about how we find voids within this simulation, we first have to accept that void shape and abundance heavily depends on how we define a void. Some void finder algorithms can range from simple spherical models to those that assume a lumpy spheroidal shape, to those that use more complex techniques, such as Voronoi tessellations and watershed transformations, to produce truly amorphously shaped underdense regions. Now for this study, I'm using a simple 3D spherical void finder algorithm of Pius et al., which approximates voids as the largest sphere enclosing some underdense region of space that meets some underdensity threshold. I don't want to dwell too long on the steps of the algorithm, but in essence, around each underdense region in the galaxy field of the simulation, we find the largest such sphere that can enclose an underdense region of space, such that we meet an integrated density contrast threshold of less than -0.8, which is a choice motivated by linear theory predictions for what the underdensity threshold of a void would be at or should be at the current epoch. Yeah. So at first it remains concentric to the void center. We do a final step at the end where we perturb the sphere in random directions to see if we can find a slightly larger sphere around the same general area that still meets the underdensity threshold. And if we do find a larger sphere, we update that as the current radius and center of the void. So our void finder results, we found 5,078 voids within the simulation, covering 83% of the overall volume of the simulation. The median radius of 4.4 little h inverse megaparsecs, and our largest void being almost a tenth of the size of the simulation box at 24 h inverse megaparsecs. Using these populations of voids, I defined 2 populations of field galaxies with which to study the observable properties of. Those 75,000 of these objects were labeled as void galaxies. Those are galaxies neither in a massive cluster nor within, or neither within a massive cluster, but are within one of the voids that we found. 527,000 of these objects were labeled as non-void galaxies. Those are galaxies neither within a void nor in a massive cluster. So before talking about the properties of the void galaxies themselves, let's look at the void radial profiles of our voids. So here I'm plotting the density contrast on the y-axis as a function of void radius. On the x-axis, where I define density contrast in its typical way as the fractional difference between the number density of particles of either dark matter particles or galaxies in a spherical shell extending out from the center of that void, and the average number of either galaxies or dark matter particles in the simulation as a whole. What we get when we use either luminous matter, that is galaxies or dark matters, as tracer particles are two distributions that roughly agree with each other, where the interiors of these voids are indeed extremely underdense compared to the average of the simulation, where that density contrast then shoots up to a maximum just beyond the radius of the void, at, again, the ridge of the void, the point spanning the void that all matter interior to is being gravitating out towards, before leveling off at the average of the simulation out at larger radii. Now, what these distributions don't agree upon, however, is that it appears luminous matter does not trace the dark matter, either interior or exterior to voids, with the interior of voids being way more, or being slightly more underdense in luminous matter than in dark matter, the opposite being true at the ridges of voids, where they're slightly more overdense in luminous matter than in dark matter. This corroborates a growing body of evidence that's kind of concerning to observationalists that show that galaxies or luminous matter in general isn't necessarily a great tracer for the distribution of dark matter within these, the luminous matter isn't a good tracer of the dark matter contents of the universe. So I now want to go on to the final portion of my talk, just looking at some of the results of the properties of void galaxies in the TNG300 simulation. So first, looking at the color magnitude diagrams for these galaxies. So here in these main panels, I'm plotting the G minus R color as a function of R band absolute magnitude, with these for non-void galaxies on the left and my void galaxies on the right. These side panels are showing the normalized probability distribution functions for my R band absolute magnitudes and G minus R colors respectively. What we see is that both distributions agree on the bimodal color distribution that we see in observations of real galaxies, with a population of brighter redder galaxies, a green valley in between, and then a peak of dimmer bluer galaxies over on the right-hand side of these plots. Some qualitative comparisons that we can make between the void and non-void galaxy populations is it appears that the void galaxy population has a less dense concentration of those brighter redder galaxies, and that the location of the peak of, or the blue peak of the void galaxies has a G minus R color that's about 0.05 magnitudes bluer than the location of the blue peak for the non-void galaxies. This difference in color is more pronounced to me when I look at cumulative probability distribution functions of the G minus R color, where we can see that very early, that void galaxies across the board appear to be slightly more bluer than their non-void galaxies, at least within TNG300. I also looked at luminosity functions and the total number of galaxies per magnitude bin per unit volume. So I fit these luminosity functions with an analytic solution known as the Schechter function, which has parameterized by three variables: m star, the characteristic turnover magnitude, alpha, the slope of the faint end of the function, and phi star, the point on the y-axis that the faint end is asymptotically approaching. We see that within these reported error bars, void galaxies have a characteristic turnover magnitude that's about half a magnitude dimmer than the non-void population, and that the void galaxy population has a faint end luminosity slope that's slightly steeper than in the non-void galaxy population, suggesting a slightly higher population of galaxies on the faint end in the void galaxy population than in the non-void galaxy population. Also looked at mass functions for these galaxies. So these are differential mass function showing the total number of galaxies per log magnitude bin per unit volume, we actually find that the median, or most galaxies in both populations have stellar masses of about 10 to the 9 H inverse or solar masses, with the medians of both populations actually being pretty comparable at about 10 to the 8.1 H inverse solar masses. Again, suggesting that these galaxies sort of have fairly equal masses, albeit less of them in the void galaxy population. For my analysis of stellar and gas metallicities within these galaxies, I first broke up my populations into 4 equal stellar mass bins, where I've labeled the lowest stellar mass bin Roman numeral 1 here, and the highest stellar mass bin Roman numeral 4. For all of the galaxies, say within this first stellar mass bin, I looked at the average chemical abundance ratios of some different constituent elements within stars and gas cells within the simulations. So plotted here are again, the chemical abundance ratios, or star metal fractions for some constituent elements within stars within the void galaxies as diamonds and the non-void galaxies as black circles. The right panel here is showing the ratio between the non-void to void galaxy points on the left axis for each constituent element. What we see is that across the board, void galaxies appear to be less metal enriched on average compared to their non-void counterparts, with the non-void galaxies being about 20% more metal enriched for all elements heavier than helium. Repeating this process for all 4 of my stellar mass bins, where plotting the lowest stellar mass on the top and the highest stellar mass on the bottom here, we see that across all stellar masses, non-void galaxies remain more metal enriched than their void galaxy counterpart, but that this ratio tends to decrease as we go to our higher stellar mass bins. So whereas the void galaxy, or the non-void galaxies in our lower stellar mass bin were about 20% more metal enriched than their non-void galaxy counterparts, the highest stellar mass bin, our non-void galaxies were only about 2 to 3% more metal enriched than their void galaxy counterparts. So I interpret these results under the idea that in lambda CDM theory, halos in less dense regions of the universe should collapse and form later than halos in more dense regions of the universe. Or put another way, the subhalos within these dark matter halos should, on average, be younger in the void galaxy for the void galaxies than in the non-void galaxy populations, which indeed, looking at medium luminosity weighted ages for these void and non-void galaxies, I find that within TNG300, the void galaxies are have stellar particles that are about 150 megayears younger than in the non-void galaxy population. So the last thing I want to talk about today are the supermassive black holes at the center of these galaxies. So here in the top panels, I'm plotting the black hole stellar mass relation for supermassive black holes in my non-void galaxies and my void galaxies, where this relation is a power law, an empirical power law that relates the central mass of a supermassive black hole to the total stellar mass of the galaxy. We see similar slopes of these power laws between our non-void and void galaxy population, suggesting these galaxies grow or accrete mass, or that the supermassive black holes at the center of these galaxies accrete mass in similar fashions over the course of cosmic time. I then looked at just the fraction of active galaxies, or active supermassive black holes, so the supermassive black holes in their active or quasar state, and find similar AGN fractions between my non-void galaxy populations and my void galaxy populations, again suggesting that no relation exists between the triggering of the AGN phenomenon and local matter and the local matter density of that galaxy. So to conclude, the location, something I've learned through this conference, is that the location of a galaxy within the cosmic web always needs to be considered when discussing the physical or observable properties of that galaxy, be it if that galaxy is in a cluster, a filament, or within a cosmic void, but that the effects that differences in local matter density have on the properties of non-void and void galaxies is still kind of poorly constrained at present, both in observations and in simulations. So here I looked at properties of void galaxies in TNG300, finding that on average, they're bluer, younger, and less metal enriched. They have luminosity functions that are a slightly better fit for the void galaxy population than in the non-void galaxy population, and that I report no difference between AGN activity or abundance between my two populations of galaxies. So with that, that's the end of my talk. Thank you all for your time, and I'd be happy to answer any questions.
Thank you, Olivia. Questions? I see many hands. Let's start here.
Very nice talk. I have one question and one comment. My question is, can you show me the slide where you explain this void finding algorithm, Pallias?
Yeah.
Well, even though you said this algorithm is from Pallias, I mean, what's the difference from the algorithm developed in 2002, Hoyer and Vogeli? I mean, to me, it looks essentially the same. 2002, Hoyer and Vogeli basically developed very similar algorithm. I think Pallias just used that algorithm.
Okay.
Okay, so please check that.
Mm-hmm.
Yes. And my comment is, you mentioned in one of your slides that your results agree with the lambda CDM theory that the halos in the underdense regions form later, right, younger. I think it's a bit absurd to say that your results agree with the lambda CDM theory because your results are from the simulations for lambda CDM cosmology. Mm-hmm. In fact, your results agree with observation data. Hoyer and Vogeli and Van de Wegaard, they show that 2004, they actually applied their algorithm to observation data, and they actually studied the properties of void galaxies. And they showed actually that void galaxies are younger, bluer, metapolar, all these things. It's agree very well with it. So your results excellently agree with observation data. That's the better thing to say, rather than to say lambda CDM theory, because there's no lambda CDM theory which actually predicts this local environment dependence. If you are trying to say, if you meant to say that excursion set theory basically says that halos with the same mass, if masses are the same, then halos should form at the same epoch, regardless of the environment. So that's the better thing, in my opinion, to say that your results very well agree with observation data.
Sure. Thank you for your comment.
I have a couple of questions about the bias. Can you show the bias in voids? You had a plot of the bias in voids. Yes, that was it. Yeah, so so you mentioned that the void inside, the bias inside the void and outside is different, but at least qualitatively, in terms of delta, which is how we usually define the bias, it's kind of similar because the galaxies are larger fluctuation. Do you agree?
Yes, I agree that it might be a bit of a stretch to say that these distributions don't exactly.
So essentially you could define bias in terms of 1 plus delta, and then you could say it's the opposite. Mm-hmm. But if you define it with delta, which is the more traditional way of defining bias, then it's actually the same inside and outside. Yeah. Yeah. But in a way, if you find difference, do you see any trend with the void sizes? In other words, different size of voids have a different level of difference. And then the other questions you also mentioned, those are different galaxies, so different luminosity function. So when you select a galaxy sample, you select a certain brightness. Is this already selected to a certain brightness? Or how is the brightness interferes with the statement about the bias? So there's two parts of the question.
Yeah, so the only, I didn't look at the bias in terms of the luminosity of these different galaxies, but that would be something interesting to look at. The only luminosity cut that I applied to my galaxies are a minimum luminosity cut to get rid of the dimmer unresolved galaxies within the simulation. So yes,
so this is a particular brightness cut. Yeah, okay.
Yeah,
so this is like what you would observe.
Yes, yes.
Yeah. Okay. And do you see any trend with the voids, or because this is one example, but what about different void sizes, depths?
Yeah, so my analysis when I looked at these plots or these radial profiles as a function of void radius didn't show much of a difference between my smallest voids and my largest voids. Yeah, so no, I didn't see a trend between those properties.
We had also somewhere there that has gone away. Then you're next.
Hi, thank you for giving such a nice talk. I was wondering if you know of the Kavli survey.
No, I do not.
The Cala Alto Void Integral Field Treasury Survey, that's what it is. So it's an ongoing survey of integral field spectroscopy of 300 void galaxies. And one of their motivations or research questions is to study the passive systems in the voids and to find out what might transform them inside the voids. Given your analysis, do you have any intuition or comments on what might make galaxies passive in the voids?
So my initial assumption would be a lack of major mergers for galaxies within voids compared to those in more dense regions of the universe. But I think I would have to familiarize myself with the Kavli survey before I could give a concrete answer on that question.
I think that might be interesting for you to look at and possibly get in touch with to have real good data to compare with your simulation data.
Yes, I agree. Thank you for the suggestion.
Okay, we have one last. Maybe the next speaker can already get ready slowly.
Just before this plot disappears, the overdense shell here looks much more dramatic than in the Sloan data that you showed. Is that because things don't fit, or is it just because you're selecting a different sort of void than in those data? It's a much more prominent looking ridge, right?
The dark energy survey data were taken with spectroscopic slices of certain thickness, which...
So there's a redshift space.
Yeah, so there might be a redshift space distortion in the void properties in the observational data that I showed earlier.
Okay, thanks.
Okay, thank you very much, Olivia.